Hello, everybody. This is 2.4, section 2.4 in Calculus 3. The topic is the cross product, which is another great operation. But this time, we will only deal with vectors in three-dimensional space, all right? So specifically to the three-dimensional vectors is this operation called the cross product, all right? So let's take a look. Okay, so what is the cross product and what is it used for? Okay, like the dot product, this is a very nice one. It's not as nice because the calculations are pretty complicated, messy sometimes, but it turns out it is very useful, and you will see that throughout the semester, throughout Calculus 3. So make sure you learn this material well. All right, section 2.4, the cross product. And again, I have to emphasize this is only applicable for three-dimensional vectors. So I have two three-dimensional vectors right here, u and v. U is the vector u1, u2, u3. V is v1, v2, v3. Not very creative coordinate names. All right, the cross product is actually really strange to define. So let me just give you the definition first, and you will say, huh? Okay, so let's see what it is. The cross product is defined, the cross product of u and v is defined as, the first coordinate is, and by the way, the answer is going to be a three-dimensional vector also. It's u2, v3 minus u3, v2, comma. And then the negative of u1, v3 minus u3, v1, comma. The last coordinate is u1, v2 minus u2, v1. And you will say, this is crazy, right? How would you ever memorize this? Of course, there is a pattern for it. And so if you have ever studied matrices, especially the determinant of a 3x3 matrix, then you would probably understand how this pattern works, okay? So over here, what I have is a sort of a 3x3 matrix. And I say sort of because it's not exactly what a 3x3 matrix looks like, right? So here in the second column, second row, you have the vector u, the third row is vector v. What is the first row? Well, it's ijk, and this is just to help you remember how the cross product is defined. Okay, so if you remember, and if you don't know this, that's okay too. But if you remember how to do row expansion to calculate the determinant of a 3x3 matrix, and some of you may have studied this, some of you may not have. If you have taken linear algebra, definitely you have. But the way it works is as follows. You take this, okay, and you multiply that by the determinant of the 2x2 matrix after you delete the first column and the first row. So that means you're talking about, of course, this part here, right? So the way it works is you do, and the determinant of a 2x2 matrix is basically this times minus this times that, okay? So this will be u2, v3, okay? So you multiply these two, minus u3, v2, and you multiply that thing with what you have here, I, okay? So that's your first coordinate. And then you go to the second coordinate, but something strange happens, right? Let me erase what I have just drawn in this now a messy matrix. Okay, so for the second one, and again, this is a very, very strange thing. In fact, it's probably the strangest thing you see in this level of mathematics. But in order to calculate the determinant, or in this case, the cross product, for the second coordinate or an odd numbered coordinate, you actually do a subtraction, negative of, oops, I'm wrong here, minus, this time you take this number and do the same thing with a 2x2 matrix after you delete the second column and the second row, okay? So what's left? What you will be left with is the 2x2 matrix u1, u3, v1, v3, and then you take the cross product, the determinant of this 2x2 matrix again. So it'll be this times this minus this times this. What did I just say? Yeah, it'll be u1, v3 minus u3, v1. okay? And then you put j because you're multiplying by this. And then finally, for the third one, you do the same thing, except now you will do k, and the matrix that you will be left, the 2 by 2 matrix, after you delete the third column and the first row, is going to be the 2 by 2 matrix left here, okay? And then you take the determinant of that, which is U1 V2 minus U2 V1. And then, of course, you put K at the end. And so that's exactly what I have here in the front, in the top as a definition, okay? So the way you remember this and the way you calculate the determinant, or the determinant of the 3 by 3 matrix, which is the cross product, is exactly this. So I would encourage you, at least for the first few times or a few days or a few weeks or forever, when you take the cross product of a two three-dimensional vectors, I would encourage you to write ijk and then fill the second row with the first vector and the third row with the second vector, and do exactly this, okay? So it'll be, watch this, okay, because it's hard to do this on video, but it's this times this minus this times this, okay? That's your first coordinate. For your second coordinate, let's do green, it'll be negative of, okay, now don't forget this negative sign. And by the way, negative signs will be all over the place, and that will be the most confusing thing in this section. Be aware of negative signs. But so you take this times this minus this times this, because remember, for the second coordinate, you're deleting or you're omitting or you're ignoring the second column, right? And again, make sure you have the negative sign in here. Right. And by the way, this, what we're trying to calculate is called the the cofactor of each of these vectors I, j, k. And this is called the cofactor expansion form of the determinant of the 3 by 3 matrix. And for the last one, the sign is positive. And what do? It'll be this times this minus this times this. Okay. So it is quite confusing. It's nothing like the dot product, which is so simple to define and so useful. This is useful. My question, and I will probably never find the answer for this, is who in the world came up with this, right? And what kind of mind would see that this is actually useful? Okay, I will answer some of those questions, not who, but but it took an incredible insight to figure out that this kind of messy thing should have a name like the cross product and come up with what's useful about this. All right, so the first thing you should remember is, remember the u dot v for any dimension is a scalar. Okay, so you get an answer, which is in the reals, right? But u cross v, as you can see, and by the way, you can write this in the brackets form like this, or you can use ijk if you like. I like the bracket notation myself, but u cross v is always a vector. All right, so make sure you do the distinction. And sometimes, because they look both they're mathematical objects, you may forget the distinction. But think of one as an animal and the other as a plant or something. These are very, very different beasts, and you have to make a distinction. So, for instance, okay, you can take u dot v, but you can't take u dot v dot w, right? Because the scalar, the product, or the dot product of three vectors, it just doesn't make sense. But you can do u cross v cross w. That would be okay, because that's a vector cross the vector. All right, so here's an example. Why are we not giving a little space here? Right. Here. All right, let's, for this u, 1, 2, 3, and 2, 0, negative 4, let's try to find the cross product here. And I don't know why I'm not here. Let's make this go down a little bit. I think I can do this. Okay. All right. Maybe you can go ahead and figure this out, right? And come back to it. And I will give you a little time to pause, and then I will give myself a little pause here. Okay, you ready for this? So this is, for I, you will do 2 times negative 4 minus 3 times 0. That would be your first coordinate. right? And then for the second one, make sure you put the negative sign, and then you do 1 times -4 minus 3 times 2. This whole thing is is bounded by the negative sign. Right, and for the last one, it's 1, 0. That's not what I meant. 1 times 0 minus 2 times 2. Okay, so it's not a very good way to write this. Right? But anyway, what is that? It's -8. Okay. Now remember, 3 times 0 is 0. It's not 3. Those are easy common mistakes that I see students make. The next one is what, right? It's, if you look at the inside of these parentheses, it's -4 minus 6, which is -10. But then you have a negative sign, so the answer is +10. Now, some people actually do this. Instead of 1, -4 times 3, 2, and then take the negative. You can also do 3, 2, minus 1 times -4, in the opposite direction, and you get +10. Finally, the last one will give you 0 minus 4, and so that's -4. Okay, so I hope you got the correct answer here, and of course, I give you plenty of times or opportunities to practice this in your homework. All right, now why is this so important? Okay, so let me give you two properties. This is because the cross product is a three-dimensional vector. It has a magnitude and a direction, right? First, the direction is extremely important. I have in this picture just a general, two three-dimensional vectors u and v on this plane, which looks like sort of a pink plane. Okay, and it turns out the direction of u and u cross v happens to be perpendicular. You can say orthogonal if you like, perpendicular to both u and v. Now, this is because of this property here. This is why this cross product is so important, because there will be many times when we will be given two vectors, or like 3 points like this, this, and this. And then we need to find we will have to find a vector that is normal to the plane, or normal to the plane defined by these two vectors, which means I need something that is perpendicular to this given plane. And the way you do that is simply by taking the cross product of these two vectors. Okay, so that is one of the major practical purposes of defining the cross product in order to get something perpendicular to a given plane. All right, and again, you will see this over and over throughout the semester, so I hope you will learn this well. All right, so u cross v is perpendicular to both u and v. Now, there are two perpendicular directions. I just happen to draw the one that goes up, but there's another one that goes down, right? And I'm saying this is the cross product is not that one. How do I know? Okay, well, there's another little thing here called the right-hand rule. Right-hand rule. So what is that? Okay, so try to, I am not very good at drawing a picture of this, but try to imagine a right hand, and you just curl up your 4 fingers, and sort of like what you see in the like icon in like a Facebook or something. Okay, is that okay? Something like this. All right, so what you do is you wrap up roll your 4 fingers from the direction of u to the direction of v. That's this direction, right? And when you do that, your thumb will stick up, and that is the direction by the right-hand rule of the cross product u and v. Now, interestingly, if you do v cross u, imagine what happens. If you do v cross u, you would have to go like that. You would have to rotate this spot, upside down, and try to do this in your right hand. Don't use your left hand, because then that's gonna mess up everything. All right, use your right hand, wrap your fingers from V to U, and you would have to turn this around and upside down. So your cross product V cross U will be exactly the opposite, okay? All right, the second thing, the direction is perpendicular and what I just described. The magnitude turns out to be, this is not something that you can easily see, but it is the Magnitude of the cross product is the norm of u times the norm of v times, well, if it's cosine, that would be the cross, the dot product, but it is the sine of theta, okay? So sine of theta times the product of the two magnitudes. Now imagine this is u and this is v, okay? Now, if you draw a perpendicular here, and this is theta, okay, what is the length of this perpendicular, or the leg, right? Well, that is the norm of u times the sine of theta, because this is the opposite side, right? Okay, so what happens, what do you think happens if you take the norm of u times the sine of theta times the magnitude of v? Now, the length of this base is the magnitude of v, right? So if you take the height and the base of a parallelogram, you actually get the, right, the area of this entire parallelogram. And I'm going to denote the parallelogram with this, small parallelogram. So it turns out that the magnitude of cross product is the area of the parallelogram in which u and v are adjacent to adjacent sides. Okay. Now, of course, this also means this is twice the area of the what? The triangle. Okay. So the triangle, of course, that I'm referring to is that triangle here. You know that the area of the triangle is exactly half of that area of that parallelogram. So keep these two things in mind, and these will come in handy as you do your assignment. Okay, so that's another little useful information. Now I want you to practice, all right? So I have this u, which is 0, 1, 1, and v, which is negative 1, 1, 2. You no longer have to draw these things. Try to find manually u cross v and v cross u. And when you have done that, you can go to the second part of this this section. Okay, all right.